Today's speaker, I'll just, if you can switch your webcam on, Robert, we'll go over to you. Hi, Robert. How are you doing?
I'm doing great. Good morning. How are you?
It's good. It's good to have you back with us. And do you want to tell the ladies and gents where you're calling from today?
I'm calling from my home base in Tampa, Florida today. It's a little bit cloudy out of there today, but I've got a nice sunny picture behind me there for you.
It is very nice. We were talking about them earlier. I know all about them, and it's. I'm sure. Even though it's cloudy, it's a little bit warmer than it is over here in Manchester. We've had
I imagine.
Storm Doris. We've had this week, and it's been blowing trees over. But it's probably nothing to compare to what you get. Okay, Robert. If you want to get your slides ready, I'll just tell the ladies and gents about next week's webinar.
Okay, will do. Thank you.
Okay, next week we have a new presenter, Len Steed from AIB International, and Len's going to be talking about root cause analysis, how it can help your food safety plan. So hopefully you will join us. I'm going to load it in the sidebar so you can register directly. If not, follow up on the emails. I'll be back for the Q&A later, but for now I'll hand you over to the capable Robert Rogers.
Thanks, Simon, and again, thank you everybody for joining. I'm seeing in the chat bar there, it looks like we have a good group from all around the world, which I'm very excited and happy to see. Thank you for joining. My name again is Robert Rogers. I'm the Senior Advisor for Food Safety and Regulation with Mettler Toledo. I've been with the organization for, well, this will be my 21st year, so I guess my career is old enough to drink this year. And what I want to talk about today is really a topic that has been a quite frequent conversation that I've had over the course of the last, maybe year and a half, 2 years, is really validating your metal detection system. I think with all the changes in regulations and food safety programs and things along those lines, I think validation is something that is certainly an important task, but I think historically it may be something that might not have been done to the full extent that some of the regulation requires. Certainly inspection systems have been in place for many, many years, and they may not have been historically validated at their point of installation. So I just want to kind of talk about some of those things in regards to validating inspection systems. So we'll first kind of talk on some key things. I think it's important to level set on definitions, and then we'll look at some different things that we might want to consider when we're validating the system. We'll give a really, really high level overview of the metal detection system and how it works. I think that's important to understand certain characteristics of the detector that will become very important during the validation process. And then, of course, we'll open up some opportunities for some Q&A, probably through the chat function. So please feel free to ask your questions through there if you like. To begin, again, let's kind of start off with just some key definitions, and I think some of the key things we want to define would be what we consider a control measure, what we consider validation, what we consider monitoring, and things like that. So I like to go by a very well-recognized group within the food safety and health globally. Would be the World Health Organization and the Codex Alimentarius. They define control measures as any action or activity that can be used to prevent or eliminate a food safety hazard or reduce it to an acceptable level. And certainly I think metal detection systems fit into this category. They will reject contaminated product from the process when they contain contamination. So, and certainly they can be set to detect down to a certain level that we could define as that being the acceptable level. So I think metal detection systems fit very well within the definition of a control measure. We talk about things like validation. you'll understand basically what level the system is capable of controlling the hazard, as well as providing the capability to remove those contaminated items from the process. So those are some of the things that we're looking at when we're validating the system. We want to understand its sensitivity or its capability, and then we're also going to want to understand what actions occur when we get a detect event. So the codec defines validation as obtaining evidence that a control measure or combinations of control measures, if properly implemented, is capable of controlling the hazard to a specified outcome. So I think the term "if properly implemented" is very important. It's a key statement. You can put all the controls in place you want throughout the process, but if they're not properly utilized or the true capability based on your production needs are not properly assessed, there will certainly be failures within that process. So, we want to ensure that they're installed correctly, that we go through activities like validation to prove their capability, and of course be documenting all of these activities to provide to outside eyes as they may be coming through during audits and things of that nature. When we look at monitoring, basically monitoring is a way of confirming what we validated is still possible. So Codex defines monitoring as the act of conducting a planned sequence of observations or measurements of control parameters to assess whether the control measure is under control. For metal detection, that's typically the checks that are conducted on the system periodically throughout the production run, where they are going to run test samples or metal samples through the system to ensure that it is still, in fact, operating correctly and detecting and rejecting correctly. So that kind of just level sets some of the terminology that we'll be using throughout the presentation. I did want to give a quick kind of look at the difference between the standard HACCP program and kind of thought process and mentality and the new HARP-C terminology, which HARP-C is the Hazard Analysis Risk-Based Preventative Controls model that the FDA is using within the new Food Safety Modernization Act. Now, I know that may be very United States-centric. However, it does affect markets globally as products that will be exported to the United States and therefore imported into the United States have to meet the same criteria. So I just want to kind of highlight what some of the more historically recognized programs under the HACCP model and how they kind of relate to the new HARP-C model. And as you can see, there is a lot of commonality between them. Certainly the hazards are a little bit different, with HARP-C also including radiological and naturally occurring and potentially intentional adulteration of products and things like that. So they're taking some of these things a step forward. Critical control points were defined in HACCP. Preventative control points defined in HARP-C. Again, very similar to one another. In fact, I think most items that were historically a critical control point would automatically become a preventative control point, but some of the preventative control points within HARP-C may not have historically been a critical control point. So a little bit of difference there, but not too much. And of course, validation, the topic that we're speaking of today, evidence of effectiveness. Evidence of effectiveness. It's exactly what we're looking for, trying to prove the capabilities of these systems, what the capabilities are, and what the final operation is going to be. And then, of course, some of the other topics in there as far as the assessments and, the timing of when we would maybe revalidate or reassess the overall program. So when we talk about validation, and we really need to determine what we are going to validate and what we want to, what sort of things we want to look at when we're going to develop our validation program. So we need to really determine what our sample size is. The POD, we would consider probability of detection. The FRR, false reject rate. So we need to kind of take all of these things into consideration when we're developing what our validation procedure is going to be, when we determine how many samples we're going to run, when we determine what our acceptable probability of detection will be, when we determine what our acceptable false reject rate will be. These are some decisions that will have to be made, and most likely they'll be made on a business decision basis based on what our production needs are to get out the door, what our risks are, what our ability to hold products should we find that there is an issue and they need rework. So a lot of these things will come in when we define these things. When we look at probability of detection, so basically validation is going to consist of running X number of passes through the system. We need to determine what we're going to base that number by, what this total number of samples is going to be based on. Certainly, one pass of the product is probably not enough. That probably is not going to provide you enough confidence that the program is truly working as you believe it to be. Is 20 passes the right number, or is it 100, or is it 10,000? I think if you only had maybe one product that you had to validate, then I could see passing a higher number of samples to gain a higher level of confidence. But if you have multiple products that are being manufactured within that environment, you really need to settle on a sample size that is going to be feasible for you to actually conduct the study. I enter into these discussions quite often with people, and they want to have the validation based on a statistically valid sampling rate. And to get a certain percentage of confidence level. I want a 99% confidence level that the 1.5 millimeter ferrous metal will be detected and rejected in the system, whatever the number is. Well, to get that level of confidence, the number of samples that you need to run can be excessive in the tens of thousands of numbers of samples. So again, if you had maybe one or two products that you had to validate on, that higher number of sampling to give you the higher level of confidence may be possible. But if you have 100 different products that you manufacture, it may be difficult to run 10,000 samples of each product and then 10,000 samples of each product with each contamination type. You can see how that can snowball into a lot of production time required just simply to conduct a good solid validation. So I think that's where industry is struggling a bit right now. What is a good sample size? And to be honest with you, I have people settling anywhere from the range of 100 out of 100, which is probably the majority of the people. But I do have some that are going as low as 30 passes. Regulation and auditors, they aren't prescriptive to say that, okay, well, one pass is not good enough, you need to do 10,000. They leave that up to you to determine what level of confidence you need in order to understand that the system is working and functioning as you believe. The other thing we want to look at here, of course, is not only the probability of detection. Is it able to detect the ferrous size? Is it able to detect the non-ferrous size? Is it able to detect the stainless steel size? The other thing we need to look at is the false reject rate. So the false reject rate is really based on setting the system to successfully run production. As we'll see in a few slides here, there are some things that can affect the performance of the detector. And so we need to understand what those effects may be and then how they're going to relate into this false reject rate. One of the things that can affect the detector as far as a product is concerned is the moisture of a product. The higher the moisture, the more conductive the product is, and the greater potential that product itself would create a defect. resulting in a false reject. So we need to understand what that level of acceptable false reject rate will be, and typically that is very low. We're talking 0.01% is a very common acceptable false reject rate. So we need to understand what those things are, what our sample size is. We're going to then calculate what the probability of detection is based on our ability to detect the material. And then we also need to understand what our false reject rate acceptable level is going to be. So that will really determine how high we can set the sensitivity of the system, and what level of risk we're willing to undertake in order to have a slight change in the product maybe create a false detect. It will certainly happen during normal production, and we want that level to be as low as possible. A high false reject rate is not a good practice. We want to have a very low false reject rate. So that's what we're kind of looking at when we're going to look at validation. We need to determine the sample size. We need to determine the probability of detection. We need to determine a lot of things before we even begin the process. But I also think that it's important to understand how the technology is going to function. Metal detection systems are used throughout the process, and there are many factors that can affect the performance. The different types of detectors here, you can see a couple of inline systems, conveyorized systems, gravity-fed type systems. They can be placed really anywhere throughout the entire production process. We need to understand what some of the factors that are affecting the sensitivity will be. And so here you can see that the metal type certainly is going to affect it. The way that a metal detector operates, it really works on a conductivity principle. So any material that has a conductive nature to it, when it passes through the detector, will result in an output. So ferrous, you can see, is both magnetic and conductive, so it's typically the easiest to detect. My non-ferrous, your aluminum, copper, brass, lead, bronze, zinc, those type materials, non-magnetic, generally good electrical conductors, relatively easy to detect. And then the most challenging material typically for a metal detector to identify, unfortunately, is probably the most prevalent material in a production environment, is stainless steel, because it's non-magnetic and it's non-electrically conductive. So that kind of gives you an idea of what effect the different metal types can have on the performance of the detector. We also will have some limiting factors such as the orientation, the direction of travel that the contamination travels in as it passes through the detector. You can see on this slide that ferrous traveling in one direction is easier to detect than if that same piece of wire were rotated 90 degrees. So we need to take things like this into consideration when we're validating it. We want to validate these systems to their really their weakest capability. I want to challenge the system so that I'm validating ferrous in its difficult position, because the other position is going to easily be detected. Well, I need to validate it when it's difficult to detect. So some of the other things that will affect the performance is the physical size of the opening. The larger the detector, the less sensitive it is. Here you can see a couple of different size detectors, and the detectable sample in the center of the opening, you can see with the larger detector is up to a 1.5 millimeter, whereas the smallest detector there, it's down to a 1 millimeter. So the physical size of the opening will affect it, and that typically will relate to where it is within the process. Obviously, earlier on in the process, we can have smaller detector apertures getting smaller metal contaminations out. But as we move further down the production line and into final packaging, and right before that product goes out the door and maybe into a case of product, now if we're going to inspect at that point, the detector has to be much larger and could affect its overall detection capability. So, again, that is going to be a factor that we're going to have to take into consideration. Fortunately, with a metal detector, there is a weakest point, the least sensitive point, and that will be in the absolute center of the opening of the detector. That is going to be truly the weakest point for detection, and that should be the area that we're targeting during validation. I want to ensure that it's able to detect the 1 millimeter piece of ferrous in its weakest area, because I know if it falls anywhere else within that detector opening, it's only going to be more sensitive, and if it detects it in the weakest area, it will detect it anywhere it falls within the product or within the space of the opening of that detector. And that's truly where we want to target not only the validation, but our daily monitoring activities. We want to challenge the system. We don't want to test the system. Testing the system may result in you having a level of confidence that, yes, it's working correctly, but if you challenge the system and know that you've done everything possible to try to make it fail, you've run the sample in the weakest area, you've run it in an orientation that is the most difficult to detect, and it still satisfies the ability to detect and successfully reject that material, that is truly what you want to be able to understand with your system. What is its worst case scenario? What is the best that it can do? Certainly, if the center of the detector is the weakest area, on a conveyorized detector running a packaged product, it may be relatively easy to access that center location and run the sample through there. Well, there are other applications where it may be a bit more challenging, as in inline or flow-through type systems, where, like a pipeline system running liquids or slurries, most people don't want to actually inject a foreign material into the actual product flow. In doing so, there's a lot of risks. Cross-contamination issues, retrieval of the metal sample. So oftentimes with pipeline or inline systems, people perform their daily monitoring activities or their daily tests by running the sample between the pipe and the detector. Well, we've just discussed that the center area is the weakest area, and certainly the location between the pipe and the detector is a much more sensitive location. So what we want to validate, or maybe validate in this application, is what is the sensitivity difference between a center mass sensitive or contamination event in the center of the detector versus where I'm going to test it on a more frequent basis on outside of the pipe, between the pipe and the detector. And we want to validate what that difference is. So we know that in the center, the weakest area, I can in fact detect 1 millimeter, but when I'm testing it outside of the pipe in a more sensitive area, the equivalent size to the center area of 1 millimeter is only 0.8 millimeters. So you can test it with a smaller material in a more sensitive area as long as you validated the equivalency of the center mass area. And again, whether that's a pipeline inline system or a gravity flow product, as we have some diagrams of here as well, we want to ensure that not only is it detecting, we want to understand what the capability is in its weakest point regardless, and then if we're going to challenge it in an area that's different from that, we want to understand what that difference in capability would be. Again, documenting all this so that when an outside third party comes in and maybe questions you on not testing in the weakest area of the detector, you have supporting reference information as to your decision and as to the outcome of capability. Certainly, the sensitivity and capability are things that we're going to want to validate, but there's a lot of other things that we're going to want to consider, and that's maybe a range of sensitivities. If you have a product that has a lot of variability in its moisture, in its temperature, in its acidity, in its salt content, all those things can affect the product's conductive nature, and therefore could affect the operation of the detector. So what some people are doing now is we're establishing a range of sensitivity. What is the lowest sensitivity that I can run and still detect the samples in the weakest area? And then what is the highest sensitivity I can run and still be within an acceptable false reject rate? And then they'll validate that through study and testing, and then they'll determine what that range of operation is, and then they basically validated that entire operating range of sensitivity, freeing up daily operation to make slight adjustments to the system without having to go through an entire revalidation program. Now the operator knows I can adjust sensitivity between 100 and 140 without having any effect on what we've validated in the past. If I have to go outside of 100 or 140, now I'm kind of working in an area that hasn't been properly validated and really is an unknown space. So this range of sensitivity is something that people are more frequently doing so that they have a little bit more flexibility during production, to where they're not having to as I would say, ride right along the edge of whether we're detecting or false detecting on product. We're also going to want to validate what happens when a detection occurs. Is the product supposed to be diverted to an area accessible only by authorized personnel? Is there supposed to be a light or a horn that sounds when we get a detect event, alerting the quality operation and management team that there was an event at that particular detector? Whatever the action is, when we get a detect event, we also want to validate its operation and make sure that it works correctly. One of the things that we look at, particularly with a conveyorized system at a point in the production where we're running packaged product, is what happens if it's a leading edge contamination versus a trailing edge contamination? Is the timing of the reject designed and set accurately enough so that regardless of the position of the contamination, the action of reject it functions regardless of where that contamination is? Another thing is, well, what happens if there's multiple contamination events right after one another? Is the air pressure and is there enough air pressure to reject that final rejected product, or did we use up all the air pressure rejecting the first three and it would miss a fourth one? These are some things that we want to look at, because again, these are all things we're doing to challenge the system so that when these events happen during normal operation, we understand to what effect they're going to have. Is the detector going to operate correctly? Does it detect the sample and successfully reject that product or that package from the production line? Probably the most important thing. We can detect things all day, but if we're not properly rejecting them, well, not sure what the sense of detecting them is if we're not going to get them off the line. So these are some of the things that we're going to be looking at validating, aside from just capability, is in fact the operation. And again, you want to look at these things from a challenge perspective. You want to give the detector the most difficult challenge for it to come up against while you're validating it, so that if those unusual circumstances were to happen during normal production, you understand what the operation and capability of the system is going to be. Validation provides you with very good information that we can use that information to make informed decisions on how to better our processes or how to make improvements. That's what regulation tends to want today. They don't want us to have a reactive mindset where we have an event and we're going to react to it. They want us to have a preventative mindset where we think about ways to prevent these things from happening in the future. Other things we might want to validate on the system is any kind of auxiliary operation that may be occurring. In this case, I'm highlighting a situation where we have a reject confirmation sensor. So a reject confirmation sensor, what it does is when we get a detect, it expects to see a package fall in front of the confirmation sensor within a certain period of time to know that we had a successful reject of that product. Well, if it doesn't happen in the right amount of time, we would get a fault or a warning. We want to validate that. We want to make sure that we're disconnecting the air pressure and making sure that an air pressure fail sensor is activated. We want to disconnect the air pressure and give it a detect event and make sure that the reject confirmation warning operates correctly. So any of these auxiliary functionalities that might be built onto the system, we want to ensure that they are in fact operating as intended, so that when that happens during production, we understand what the activity and action is going to be, and we can confirm its proper operation. So this is just a quick little animation. We can see that the air pressure is maybe not going to work. We get a contamination that comes down the line. It gets detected in the detector, but because the reject did not operate successfully, the reject confirmation sensor was never triggered, and therefore in this case, the fail-safe system was to shut the belt down. We would want to make sure that that happens. We would want to validate that that operation does in fact operate in that way. We also want to make sure that this package is stopping before it's going on to the takeoff conveyor and getting pulled away, and that contamination now makes it on down the line. So there's some other things that we can look at when we're validating the systems. So here's another kind of short example. Looks like everything's going to work correctly. I don't have my X over my air pressure anymore. So see if the animation runs, and let's see what happens. We got product coming down the line. It looks like we have a contamination. We get a detect. We get a reject. We get a confirmation, but the reject kind of bounced out of the bin, and now there was an unexpected package on the line. So we have another sensor here that basically is counting the number of packages, and it knows how many packages should pass this sensor. In this case, it saw that there was an extra one because the contaminated one was not successfully rejected 100%. And so therefore we have an unexpected package on the line as the warning. Any of these sort of auxiliary functionality, air fail systems, beacons that light up, or horns that are supposed to blare whenever we get a detect event, we want to validate the proper operation of all of these parts of the system as well, not just sensitivity, capability based on false reject rates and all that sort of stuff. We also need to validate the successful operation and all of the fail-safe devices that may be included within the system. That last animation, probably not a very common scenario where product bounces into a reject bin and then bounces right back out of a reject bin. Well, unless maybe if the reject bin is already full of product. We have a bin full sensor in there to indicate when the level of product gets to a certain level, we want to alert the user. So we want to validate that that sensor is also working. The reality, folks, is if you're having this much contamination in your reject bin, something else is probably wrong that we need to stop and figure out what's going on. But talking validation, any of the auxiliary items we want to validate. So kind of closing things out, we want to validate capabilities. Well, first we need to understand, number one, what our hazards are. What is this device, this control measure? What is it being put in place to satisfy? Are we trying to detect just metal? Are there other foreign material risks that we are concerned about? Those answers are going to lead us into what control measure should be in place to protect against that hazard. Then once we've defined that control measure, well, now we have to determine what its capability is going to be. So how small of a material can it in fact detect successfully? We're going to do that action through validation. We're going to do a series of tests. We're going to run series of samples through there based on what our desired sample size is, what our acceptable false reject rate is going to be. All these sort of things are going to come into play. We're then going to perform the validation activity by running a series of samples through the detector, determining what its capability and operation capability is going to be as well. To validate it, we're going to, of course, document all that information so that when somebody may come in at a future date and question whether or not we validated the system or why we chose to test it with a 1 millimeter ferrous versus a 1.2 millimeter ferrous. These are all things that will act as supporting information for those questions from outsiders when we, have somebody coming in and asking why we're doing something in a certain way with our product. We also want to validate, again, the operation or any auxiliary functionality that may occur. When a detect occurs, XYZ is supposed to happen. We need to validate that XYZ is in fact happening and working correctly. So this last screen here, I just want to point out our website, www.mt.com. Please feel free to go out there and look at it. There's all kinds of great information out there. We have all kinds of different white papers, technology guides. There's different webinars that we've put on ourselves. And of course, as I'm sure you're all aware, the great resource that IFSQN is through their events such as this, through their recorded webinars and whatnot. Just fantastic information out there. And I will now, I guess, open it up for questions.
Yeah. If you can stop sharing your screen, Robert, and we'll get you on webcam and we'll do the Q&A. Fantastic overview as usual. I especially like the little animations that really help you visualize, what you're talking about, really, especially for a layman like me. So yeah, and it shows you that, the layers of detection that you've got there, and the way that the system all works together to support foreign body detection and elimination, really. There's been lots of questions already, so we'll dive straight in there, Robert. And I'm scrolling down to an earlier one from Osama Ismail, and he says validation stages: 1, design qualification; 2, installation qualification; 3, operational qualification; 4, performance qualification. Which one we are discussing today? Oh, sorry, your microphone's not on, Robert.
How's that, better?
Yeah, that's better, yeah.
Sorry, must have hit the button.
Okay.
My answer would be yes to all of those. Validation, really, when you're looking at design qualifications and things like that, that's really kind of where we're looking at determining, okay, what does the detector look like? What size do I need? What products am I going to run through there? The installation qualification and operational qualification, I think within those layers is really where validation sits. I like to validate systems, number one, kind of at the design stage to understand what the capabilities are going to be and understand whether it's good enough or not. And then certainly at the point of installation, go through another installation qualification that has some component of validation in there. And then again, the operational characteristics. Okay, what is happening when we get a detect event? And again, so I think validation falls kind of in all of those stages. We typically do validation at the point of installation, but prior to implementation of that control within the process. So obviously we need to install it in the process and understand in factory at location how all those things are going to affect the operation. So there's some things that we can't necessarily validate in a laboratory, let's say. But so to answer the question, I think it's really validation can be a component in each one of those stages and should be a component in each one of those stages.
Okay, thanks, Robert. Dana is asking, we have a metal detector that does not recognize the test probes directly on the belt, but when you put through with a box product, they are recognized. Why is this?
Okay, so I mean, there's many reasons as to why it may or may not be working correctly, for sure. Just kind of off the top of my head, there are conditions where basically with a metal detector or any inspection device, you have a threshold. So once we hit that threshold, that equals a detection. With a metal detector, that threshold is monitored as a voltage. When a size of contamination goes through there, it creates an output voltage. The bigger the contamination piece, the bigger the voltage. The more sensitive location that it travels through, the bigger the voltage. So basically, this threshold needs to be satisfied in order for a detect to be registered. Well, in some cases, the product itself can have some level of conductive nature to it or some signal that it generates. So it's helping me meet the threshold. So it's kind of the product plus the contamination that creates the end result. So that's oftentimes what we see when that's the situation. Whenever you're running whether it's validation or a monitoring activity, whenever you're running a test sample through the metal detector, you always want to do it with product because that's what you want to protect. You're not worried about if a contamination happens to, run on the belt when there's no product running through there. You're worried if there's contamination within the product. So that's really what we want to challenge it with, because there are some products out there that will actually do the opposite, that will cancel out the signal of the metal when they're run with the product. But if we just run a metal sample through there, it detects it just fine. So it may give us a false sense of actually what is happening on the system.
Yeah. Okay, great. Warapun is asking 304 or 316 SUS. Which one is easier to detect?
Yeah, so typically, and again, there isn't a blanket answer to say one or the other. Product effect can have an effect on how it detects the different metal types. Typically, 316 is what most people use. I see 316 as a slightly easier to detect value of stainless steel than 304. Typically, the higher you go in number, you got 304, you got 316, you have 440. The higher you go in number, the higher the level of I think it's chromium in it that is the detectable level. So as that number increases, that chromium level is increased, and that is an increase in ability for it to detect. I would say typically people are using 316 grade as their test piece, if you will, though. Okay. But certainly it should be based on whatever stainless risk material there is. If it's 304 in the facility, test for 304. If it's 316, test for 316. If it's both, test for both.
Yeah, good point. Eduardo, how often should the software in the metal detector be updated?
So the software itself doesn't really affect performance per se. So it's not like over time the software is now a little old, so it's not as sensitive as it used to be. More so, software updates are functionality based. So it might have some user screens that are available in newer software versions than they are in older software versions. Excuse me. I mean, I have detectors out there that are still operating on our version 1 platform, which had absolutely no communication capabilities, but it's still a great metal detector. As people in today's world, we like to get a lot of data out of our system, so we do like the communication capabilities. We do like some of the extra functionality that's available in newer software. So from that perspective, that's really where we base software updates, is if you need a new functionality, software update will do it. There's not a whole lot of software updates that are focused around capability.
Yeah. Do systems like, well, for example, yours, can you link them into modems and dial in and see how they're working and things like that?
Yeah, to a certain degree. Certainly the ability is there. The acceptability from facilities often isn't there. They are very, facilities are very kind of hesitant of letting people, especially in today's world, kind of get into their system. So the capability is there. A lot of times it's based on the facilities acceptability of us coming in and looking at those parameters. And certainly that can be done as on an ad hoc period. I'm not going to have full access to their system. I'm only going to have access when they allow me to. But that capability is certainly there.
Yeah. Farzad, if one product rejected by the metal detector in the first run, but not rejected in the second and third run, what should we do?
Well, I have an expectation when I have gone through and installed a system and validated it, and I now understand what its true capabilities based on, the best case scenario of my product and the worst case scenario of my product. I kind of, that's why the validation procedure is very important to understand what that difference is. If somebody were to say, hey, I'm getting when I run my samples through there, I'm only detecting it 25% of the time, I would say, well, either the system isn't set up correctly because it's not detecting it 100% of the time, or it's not capable of detecting that size sample. And I would say that that's, not an acceptable level. 100% is impossible. We're dealing with electronics, we're dealing with environments, we're dealing with product variations that happen batch from batch, piece to piece. So 100% is never going to be possible, just like zero contamination is not, it's not feasible. So you want to have the highest level of percentage of probability of detection through that validation, and that's why we want to run more than just one sample to say, hey, I validated the system. No, because all these variations. And really, I think validation should be done over a period of time as opposed to a point in time. I might do an initial short-term validation snapshot. Here's what we believe the capabilities are. Now I'm really going to assess production and operation over the course of the next 3 months and collect all of that data and use that as my true. Now you might be able to feasibly determine a 10,000 sample run, which is going to give you that highest level of confidence.
Yeah. Because then over that period, you're going to see a lot more variation in people, materials, temperatures, all sorts of things. Yeah. Okay. Hinwai, is a 4mm test piece for metal detector normally used to verify the metal detector?
The piece size goes everywhere. I've got some facilities that are inspecting down to, below 0.8 millimeters. I mean, it's smaller than a grain of sand. But then I have some facilities, depending on the application, depending on the product, depending on where it is within the production, that are up even over a 7mm size. And people may be familiar with the FDA's consideration for a choking hazard as 7mm in diameter. So there are applications where even 7mm isn't possible because of the size of the detector that's required to run the product at that point, the conditions of the product at that point. Oftentimes that's not from a food safety perspective. Those systems that are detecting the higher levels or much larger contamination sizes, most of the times those inspection systems are placed right before another piece of equipment, and its only purpose is to make sure that there's no large contamination in it that may damage that next piece of equipment. So it may be right before a filler or right before a grinder or right before a mixer or something like that. We're not really protecting the end product, we're protecting the equipment from damage.
Okay, clear. Martha is asking, what sort of rejection mechanics are usually used for 44-pound bags of dry product where it's hard to push and requires a large bin?
Yep. So I've seen, in my 20 plus years experience, I've had the opportunity to visit many facilities and certainly the systems that I've seen design coming out of our facility. So there's a lot of different choices. Sometimes what we can have is we can have a retracting band where the conveyor belt actually retracts on itself, providing a gap then for the product to fall into. And I've seen where it's maybe even down on a slide and it slides down to a different area within the facility. I've seen just an end flap where basically the end of the belt is going to flap down, and now the belt can, or the bag can slide down there. Yes, pushing that product and physically moving it and diverting it can be challenging because of its size and its weight. So oftentimes we change the direction of travel as opposed to trying to force the product to move its direction. If that makes sense, I hope it does.
Yeah. Yeah. Okay, Sylvia, if the units are 50 kilogram sacks, so I need a big arc metal detector for the units going through, is there any way to reduce the sensitivity? The current metal detector is 3FE. Well, you can see, hopefully you can see that.
So, I mean, obviously the size of the product is going to really dictate what the size of the metal detector needs to be at the point of inspection. So if you're wanting to inspect while that product is in the bag physically, well, I can't really shove a 55-pound kilo bag through a small detector. It just won't physically fit. So to a certain degree at that point, I'm really, it's not necessarily what the capability of the detector is, it's what the product allows me to do. Now, if you're a facility that says, well, I've done an analysis in between where I'm filling the bag of product and I've closed the bag and then I'm now metal detecting. In that space, I've identified that I don't have a whole lot of risk for further contamination. Maybe what we do is we run it through a gravity-fed detector while the product is being filled into the bag. So now, rather than having a detector that'll fit a 55-pound bag of product, I'm only having maybe a 6 or an 8-inch diameter detector where that product is flowing through as it's being filled into the bag. So there's a lot of different choices that we can do, but we will be limited on not necessarily what the detector can do, but what the product allows us to do.
Yeah. Okay. Just a couple of questions I can answer, actually. Margaret, are the on-demand webinars free of charge to food manufacturers? The Metal of Toledo on-demand webinars are free of charge. That's correct, isn't it, Robert?
That is correct, yes.
And all Food Safety Fridays webinars, and Robert's done a fair few of those, are free also on the IFSQM website. Sarah's asking, could you show the Hassett versus Harp C slide again? Well, you'll get the slides, Sarah, so you can see those at your leisure. John's asking, what are your thoughts on metal detectable belts? Are they value for money?
So when people are doing things like metal detectable plastics and metal detectable belting and things like that, they're great things. I don't take anything away from the manufacturers that manufacture those items. I think they are very, very important within our industry. However, I think it is very important that when somebody goes through a process, decision process to say, hey, we want to replace our belting with metal detectable belting or our plastic with metal detectable plastics, you want to understand what that true level of detection capability is going to be in your particular situation. Because again, all the different factors, the factors of product, the factor of detector sizes, all these different things that play into the mix. Just simply because it's metal detectable belt does not mean that if a scraping of that belt were to happen and it's a very small piece of that material that may be a concern to you is going to be detectable. So we want to understand what that level is going to be. Typically when we're talking about those different materials, historically with metal detectors anyway, in metal we talk spherical sizes. So 1 millimeter, 2 millimeters, 3 millimeters in kind of that range of sizes. When we talk about metal detectable plastics and X-ray detectable plastics, now you're typically talking about cubed sizes. So 1 centimeter cube is really what the detectable level is of those materials. Again, it's not a piece of metal. It's a piece of plastic that has some materials embedded into its ingredients that are conductive. It doesn't turn it into a metal belt. We wouldn't want it to, and now that thing's going to rust and all these different things. So, I mean, I can't give you a level of detectability on that belting material. I do think that there is, they are valid, that it is a important component in certain applications. But before you go through a process of just, hey, let's replace it with metal detectable belting because it's available, understand to what level you're going to be able to detect that belting and see if that's worth the investment.
Yeah. Okay, Sylvia, is it accepted by BRC to validate metal detector by their own users? Does that make sense to you at all?
Yes. So I'm very familiar with BRC requirements as well as most of the GFSI recognized programs. And when they talk about things of validation, oftentimes they don't necessarily dictate who that is. They want that person to be qualified. So if that person has qualifications through experience, through trainings, through whatever, no, nobody's going to say that, Mettler Toledo has to come in and validate a Mettler Toledo metal detector. Really, anybody could go through that process. They may have to provide some supporting reference as to their ability to do that and their experience and how they're qualified to be able to conduct that activity. But I don't think there's anybody that would say that, no, you can't do it because you're not the manufacturer.
Yeah. I guess once you've done it once, if you've got a standard operating procedure that's maybe done in conjunction with your supplier, then can you just carry on doing that?
Yeah, I mean, really, depending on the organization, I think like the new FSMA requirements, I think their validation timeframes like every 3 years. I think BRC may have it written that they want it every year or after a significant change within production. So there are triggers as to what may trigger a revalidation, but yeah, I'm kind of under the umbrella that says, as long as you have the experience and the knowledge and you know what you're doing, you're qualified to perform that validation. So yeah, I mean, anybody can and should do that.
Okay. Eileen, we recently had a piece of copper from an electrical wire that our metal detector failed to detect when it's used to detect even dot size piece of metal. Why is that?
When you talk about wire, a couple of things could be orientation. Again, in one direction of travel, it will be easy to detect, and in another direction, it will be more challenging to detect. So it could be something along those lines. When we talk about diameters of wire and orientation, if the diameter of the wire were the exact same spherical capability that that detector has, it doesn't matter if it'll detect it as soon as it goes into the aperture. But if that diameter is smaller than what we're able to detect with the metal detector spherically, now it's going to depend on how long this piece of wire is. If it's less than 1/3 diameter of the spherical capability, it doesn't matter how long the wire is. It won't detect it. Those are just limitations really based on the physics of how metal detectors operate. So it's hard to say in that particular situation. It could be something to do with orientation effect. I'd say if you try that piece of wire and change its direction of travel and see if it's able to be detected. If it's not able in either direction, there may be something there. If it's got a consistent spherical capability, you're going up there daily and testing it with your challenge pieces and you haven't noticed anything, no problems with it being able to detect or reject those, I would say that we're probably on the verge of of the limitation of what it is in fact able to detect at the particular setting that it's set at.
Okay, we've got a bit of a problem here, Robert. Questions are coming in faster than you can answer them. So it's going to be a long day. What I've done is I've loaded the certificate in the sidebar for those who want to need to leave. But are you all right to carry on for 5 minutes or so?
Yeah, sure.
Okay. All right then, Jennifer, I understand how to validate existing equipment to confirm its capability, but what about validating that your equipment is aligned to industry best practice?
That's an unusual question that I have not been asked before. If I understand it correctly, so we talk about things like industry best practice. That's not necessarily talking about capability. That's more talking about operation. So one example would be a stop belt reject. So if I have an application where I get a detect and the reject operation is simply the belt stopping, that may not be as good of a design or practice as would a system that would physically divert that product to a secure area accessible only by authorized personnel. It's just simply stopping on the belt. Well, how do we ensure that somebody just doesn't have the ability to start the belt again? How do we make sure that they are, in fact, removing that package off of the line prior to restarting the belt? So when we talk about things like industry best practices are going to be based on practices and design as opposed to capability. So I would say that it's more so ensuring that industry best practices as far as design is concerned, physically diverting product to a secure area accessible only by authorized personnel is a big thing. The communications capability and data collection capability is becoming more and more of what we would consider industry best practice as we're tying these systems into existing factory management systems and data collection systems. Certainly those are leaning towards what we would consider today industry best practice type designs. The detection capabilities, they're based on physics. So my systems that are 20 years old, there's not a whole lot of difference in capability than the systems I sell today from a detection capability standpoint. Certainly you may see some improvements in detection capabilities based on detector design. They're less immune to interferences and electrical interference noise within the plant environment. They're more stable to vibration. But as far as how they operate on a physics principle. And unless we can change physics, we're not changing how those things operate.
Okay. Ricardo, when buying a metal detector, how do you choose the type of rejection?
There's a lot of considerations when we talk about design of systems. A lot has to do with space within the insertion space within the production environment, where it's going to go within the process. Pretty much it's one of the areas where Mettler-Toledo does a really good job is in the product handling aspect. I don't think I could count the number of different reject designs we have for different applications. Anywhere from a stop belt to an air blast, a pusher, a diverter, a retracting belt, an end flap conveyor. There's any number of different things. A lot of times those are decided when we're really going through the design stage. When we understand what the product is, we understand what the application is, we understand the space that it's going to fit in. Now we're going to throw out a few different choices there of the overall design and how we want it to operate.
Okay. I'll just take a few more. I know we're pushing on. Morad, is there any reference to validate my metal detector? Any references?
So that's and again, these questions have come up quite frequently over the course of the last few years, more and more, I think, as regulations have changed. But there isn't any scientific document per se. Oftentimes we talk about things like validation in the space of food safety. We combine things like validating a metal detector to validating the kill step to kill listeria in this particular product. Well, there very well may be educational reference, journal reference for things like killing E. coli and killing different bacteria and microbiological type concerns, because there has been extensive studies over time with that. There's not necessarily one or multiple references for metal detection principles. There are great guidebooks out there. We have some great guidebooks through Mettler Toledo. I know we've worked very closely with some of the different food safety organizations like BRC to help them develop guidance documentation around this sort of stuff. So, it's tough answer or question to answer directly, but there isn't any scientific journal or document. There's a lot of reference material, and that's really what it acts as. I wouldn't say that you would be able to, if somebody said, hey, show me the validation of your metal detector, and you pull out a reference document and say, well, based on this reference document, this is the plan we chose. I don't think that would be enough. I think that reference document is simply supporting documentation, but you do need to go through the action of, performing a test.
Okay. The next two questions are actually very similar, Barbara and Sylvia. They're asking about, Sylvia, 25 times with the sample test piece, does this seem right? And Barbara, 30 passes, is this a sufficient sample size to give confidence? So they're related, really.
Yeah. I mean, I would say that probably industry average, those are probably safe numbers. Very common numbers, and if you look at it from a statistical standpoint, however, there's almost no significance to 30 passes or to 25 passes. In order to gain any kind of significance, we're talking up in the hundreds to multiple hundreds of passes. I think 95% confidence level, plus or minus 2 or 3. You've got to run a sample size, I think, of 330 passes. Well, that's 330 passes of product for your sensitivity, and 330 passes of your ferrous, your non-ferrous, and your stainless steel. Oh, and on pass number 200 or 329, if it didn't work, well, now you have to start all over back at 0 again. So, I think that's why people are kind of settling. Well, 30 is possible. It's feasible for me to do that. I can handle 30. Statistically, It's really no significance. That's why I kind of look at, hey, let's look at this 30 as kind of a short-term validation, and then let's continue to monitor our activity over the course of the next several months, where we're going up there and testing it every day or every hour with the test samples. Let's collect all this information and really do that activity the same way, where we're targeting the center of the detector, the weakest area, as opposed to just letting them throw the card on the belt or something. Let's go through this 3-month period of time where we're really, really looking at challenging the detector every time we touch it, document that, and use that as your longer term validation that provides a higher level of significance. Okay.
Right. I think we're going to have to call it a halt there. I mean, I could scroll up and up and up, and there are dozens of questions. I think what we'll do one day on a Food Safety Fridays or something like that is forget the PowerPoint and just have an ask the expert.
Yeah, just do a roundtable.
Just do a Q&A. Because every time you come on, there's just, don't get me wrong, you answer lots of questions and absolutely brilliantly, but we never get through them. So it's obviously a real, it creates a lot of questions in people's minds, and they struggle with it, don't they?
Yeah.
Okay. All right. Well, Robert, you're brilliant. You're fantastic. You are the world expert on metal detection systems, without any doubt. We say it every time. So thanks on behalf of the IFSQ and myself and everybody here today and sees us in the future. And no doubt you'll be back in the future. I really hope you will be.
Very much. Thank you very much. I really appreciate what you do for the industry as a support method, and, providing us the opportunity to get the message out there so that we can answer some of these questions for some of these folks. And, we really do appreciate the work and the efforts that you put in as well.
Yeah, we'll try and bring it all together, and we really will have to get thinking caps on and do something to try and get some more answers. Right, all right, Robert. Have a great weekend, and I'll see you again. Thank you.
You too. Thank you. Thank you.
Cheers. Bye. Okay, ladies and gents, that's it. I did load the certificate in the sidebar earlier. for those who needed to get away. You can grab it now. Just click on the link. It takes you to a page on the IFS Scrum website, and then on the right-hand sidebar, that'll take you to Dropbox where you can download it. People keep asking. You can either print that certificate and write your name on it, or you can open it in a graphics package such as Paint. I don't have the time to individually personalize everybody's certificate. I'm sorry about that. We'll be back next week with Len Steed from AIB International, and next week's webinar is root cause analysis, how it can help your food safety plan. So I'm sure obviously root cause analysis is vital to get into the nub of your problems and identifying preventive actions to improve your food safety system. So I'm sure that'll be a great presentation with a new presenter. Today's webinar has been recorded. I will issue the slides and the certificate and the recording by email to everybody that registered. And I did see in the sidebar somebody said they've not been getting those follow-ups. I will check that and get back to you. So great, fantastic. Metal of Toledo and Robert Rogers today. Excellent, and we'll have him again real soon. It's Friday, the best day of the week. Enjoy your weekend, be safe and rest up, and we'll see you all next week. Take care.